Yes, let me introduce our lecturer today. So I'm very happy to see that so many people have come. We have a fantastic lecturer. We have Joel Tropp from Caltech CMS. He's an expert in many areas, including applied mathematics, data science, machine learning, numerical linear algebra, randomized algorithms, randomized matrix theory. Some of his best-known contributions include matching pursuit algorithms, randomized SVD algorithms, matrix concentration inequalities. He has won several awards, including, for instance, being recognized as a highly cited researcher in computer science from 2014 to 2018. He's the co-founder and section editor of the Siam Journal of Data Science. He was also one of the co-chairs in the first edition of the Siam Conference of Mathematics of Data Science. And he was elected Siam Fellow in 2019 and IEEE Fellow in 2020. So yeah, we're very excited to have Joel Tropp today. So let me welcome this Joel Tropp.
Good morning, welcome. Thank you for coming. Is this on yet?
I think it's on, yeah.
The mic's on? Great. Okay. So what are we talking about? So the one-sentence summary of this course is that randomized algorithms are powerful tools for solving linear algebra problems. And the way that we're going to organize this series of lectures is into a pattern that I call themes and variations. So the idea is that I'm going to tell you about different conceptual ways in which probability can be used to design algorithms, and then I'm going to show you a couple examples of each of those patterns of use. So those are the variations. Okay, so to get started and to wake you up, I have an activity for you. So what are some randomized algorithms that you know for any kinds of computational problems? So please talk with your neighbor about this for a minute or two, and then we will, no, I'm serious. Talk to your neighbor for a minute or two, and then we'll see what we find out. All right, let's reconvene. So, who wants to share some randomized algorithms? Yeah? Yes? Randomized SVD, all right. This is a linear algebra algorithm which involves randomness. We're going to talk about that on Wednesday, tomorrow. What else?
Stochastic gradient descent.
Oh, great. Stochastic gradient descent. So what does stochastic gradient descent do?
Find the minimum of the function.
Yeah, how does it do it? Okay. It approximates the gradient by a random vector that's correct on average, and then takes a step in the direction of the random gradient. And what does it accomplish? At each step, it typically moves a little closer to the objective set. To the solution set of the optimization problem. I'm not awake yet. That's a form of progress on average. So we'll talk about some linear algebra algorithms in the spirit on Thursday. More examples. Yeah.
Randomized rounding of linear programs.
Ooh, randomized rounding. Excellent. So how does this work? Well, we take a combinatorial problem, we replace some of the difficult constraints with weaker convex restraints, we solve the optimization problem, and after we're done, we use randomness to map back to a solution that's pretty good on average to the original combinatorial problem. Beautiful approach. We won't be talking about this, however, but it's one of the most remarkable approaches to solving optimization problems and combinatorics. What else? Yeah.
Random projections.
Random.
I'm thinking particularly in the context of LPs, SDPs.
All right, so I'm going to write down random dimension reduction. So how does this work?
You have say a problem with a lot of constraints. You're going to aggregate those constraints somewhat randomly, but in a smart way. That's going to give you a problem that has way less constraints. You solve that, and then you lift the solution back to the higher space.
Yeah, exactly. So this is a form of randomized dimension reduction. The idea being we're going to take a big problem, we're going to squash it so that it's easier for us to solve computationally, and then we're going to hope that the reduced problem somehow still gives us a pretty good solution to the original problem. So this is called dimension reduction. We'll talk about patterns of dimension reduction in linear algebra on Friday. What else? Anything else come to mind? Yeah.
Ensemble-Kalman method.
Ensemble-Kalman. Is there any randomness in the algorithm?
Well, you keep sampling like random noise adding to the random ensemble.
Ensemble-Kalman. Got it. Sorry, I was thinking about vanilla Kalman filters, where you instead think that the model for the data is random. You think that there's some process you're trying to track that's being driven by white noise. This is not an example of algorithmic randomness, whereas as you're saying, these ensemble-Kalman methods and other kinds of particle methods may actually use some sort of randomness to generate random walks that hopefully will give you some distributed overview of what the distribution looks like. Great. What else? Justin.
So, dithering, or randomized quantization and signal processing?
Dithering. Yeah, so when you print something out on your laser printer in black and white, it would like to approximate gray tones, and it does so by using patterns, which are sometimes generated at random to approximate the exact shade of gray that you're hoping to reproduce. This actually comes up in linear algebra as well. Sometimes people do randomized rounding instead of deterministic rounding, like in the IEEE standard. And this can actually reduce floating point errors. Okay, great. So it's kind of interesting to hear what y'all think of when you think of randomized algorithms, because these are much more on target than a lot of the things that people often teach in linear algebra, which include things like Monte Carlo integration or quadrature, where you approximate an integral by sampling, or MC-MC, where you try and sample from a distribution by driving a Markov chain toward that limiting distribution so you can get a sample from it. Or in computer science, there are a whole bunch of randomized algorithm templates that also didn't turn up here. So it helps for me to know my audience, understand where you're coming from. Okay, thank you so much. So a few of these are linear algebra algorithms, and that's going to be our focus here. I'm going to be interested in solving basic linear algebra problems. And you might think we already know how to do that, and that is correct. We are actually very good at solving basic linear algebra problems. But some of the existing methods are not as scalable as we would like. They might be brittle or robust. They might, not so robust. They might have trouble solving the most challenging problem instances. And then there's some things that they just can't do at all, which is kind of vexing. So the idea which has emerged really in force over the last 20 years or so is that by designing randomized algorithms for linear algebra problems, we might be able to accomplish things that we couldn't before, or we might be able to develop algorithms that are more computationally efficient, like the randomized SVD, which is based on matrix multiplies, which are super fast. So there are lots of things we might hope to do. And this has not historically been the perspective in linear algebra, where people used to think that randomness was sinful and that it was to be avoided at all costs. So my hope is just to give you some idea about the ideas rather than focus on specific algorithms and their use. All right, let me pause for a minute if y'all want to come on in, if there's anywhere to come. Are there any seats left? All right. Okay, so let me start out with a simple example just to warm up. Example 1, verifying matrix multiplication. So we're going to let A, B, and C, 2 underscores means a matrix, be square matrices with integer entries. Okay, square matrices with integer entries. And the question we would like to answer is C the product of A and B? All right, so what's the simplest way to approach this problem?
Check every entry.
Yeah, we can multiply A and B and look whether we got the same thing. And this is an n-cubed algorithm. Matrix multiplication is usually n-cubed. I suppose that if you're a theoretical computer scientist, you would tell me that it is n to the 2.35 or whatever. Okay. All right. Could we do better? So the answer is yes. There's a classic strategy which comes from computer science for checking polynomial identities. So let's see how this works. So we're going to choose a random vector, x, 1 underscore means vector, which has independent entries equally likely to be plus or minus 1. Okay. What are we going to do with that vector? We're going to multiply it into C, and we're going to multiply it into AB. So why can we do this more efficiently? Because we can associate. So first we multiply x into B, then we multiply the resulting vector into A. And so how much does this cost? This is at most an n-squared operation. Okay, so this is already faster than any form of matrix multiplication that we know. And then what do we do with Cx and ABx? So if they are not equal, what do we conclude? These two vectors. Then we report false, right? And could we possibly have made a mistake? No. So if this algorithm tells us that C is not the product of A and B, we can be confident that that is in fact the case. If they are equal, we report true, maybe. So is it possible that Cx equals ABx, but they aren't the same? Yeah, sure. It could happen, for example, if the matrices have a big null space or something. Okay? So the fact is that it is very unlikely to get the answer wrong. This is something you could quantify if you wanted to. And so even though you might make a mistake in reporting true, it's uncommon. Okay? So if you wanted to amplify your success probability, you could repeat this process a number of times. And this is an example of what's called a Monte Carlo style algorithm. Because it is probabilistic, and sometimes it produces the wrong answer. Okay? Great. Any questions on this example? Yeah?
Does it matter that x is exactly plus or minus 1?
No, it doesn't. I'm doing everything discretely because then you could actually count the number of ways you could get this right or wrong, which is usually the way that people approach polynomial identity testing. You could do this over any ring you like, so reals, complex, whatever. Yeah, and you could choose different distributions. Okay. This is a setting where you could get the wrong answer, though. That's one of the reasons I did it this way. And it's pretty easy to see you could get the wrong answer. Okay, more questions? All right, let's talk about an, and I would say that this arguably is a linear algebra problem. It's not one that we tend to think of that often, but it does involve linear operations on linear operators. Okay, here's another example, which has a different spirit. This is the maximum eigenvalue problem. So in this case, we're going to let A be an Hermitian matrix that is positive semi-definite. So that means real symmetric, all eigenvalues non-negative. And our goal is to compute the maximum eigenvalue of A. Okay, so how would you go about solving this problem? How did you learn to solve this in your first linear algebra class?
Power method.
The power method. So what does the power method do?
Just multiply by A over and over again.
Yeah, we take a vector and we multiply it by A over and over again and hope that that drives us toward a maximum eigenvector. So let me be a little more specific. What vector do we start with? Yeah, the usual prescription is to start with a random vector. So we'll do that here. So we're going to draw x, which is a normal vector with mean 0 and identity covariance. So all the entries are independent and standard normal. And then we are going to repeatedly multiply to form the vectors a to the tx. We can do this the same way we did a minute ago. We multiply first by a, then we multiply again by a, and then again by a, and so forth. And our eigenvalue estimate will be a little bit complicated because I'm not adding the extra notation here. It's ct, which is the Rayleigh quotient of a to the t against a to the t minus 1x. Okay, so this is effectively what the power method is reporting as your maximum eigenvalue estimate at each step t. And in fact, with probability 1, this converges to the maximum eigenvalue of A. Okay, that's cool. So this is a randomized algorithm because there's a randomized starting vector. And it's guaranteed to give us the right answer eventually. Okay. Now, practically speaking, we do not run algorithms forever. Otherwise, they are not algorithms. Algorithms must halt. So we stop after some number of steps. And we would like our estimate to be relatively accurate. We'd like to be close to the maximum eigenvector. Do we know how many steps that'll take? It depends. Yeah. It depends on a bunch of stuff. We don't really know. So this kind of algorithm has a random runtime. I've run out of space, so I'm going to put this up here. Random runtime. Because we don't know how many steps it'll take to get to a specific level of accuracy. Okay? And these are called Las Vegas style algorithms. Those that always give you the right answer, but might take some unknown amount of time. So the runtime is a random variable. So these are the two basic classes of randomized algorithms that folks study in randomized algorithms classes in computer science. And I've just shown you examples in the realm of linear algebra rather than the more discrete examples that people often discuss. All right, any questions on these? So the goal here is really just to illustrate that randomness does have a role to play in linear algebra. And in fact, you probably already are familiar with some form of these algorithms, randomized identity testing and the randomized power method, where we start the power method with a random vector. So we're going to talk a lot more about the randomized power method tomorrow. For now, I just wanted to emphasize that it is very important that we pick a random input here if we want to ensure that we get the right answer for an arbitrary matrix. So unless you already know the maximum eigenvector, you're going to have trouble solving this problem. So there's a chicken and egg issue here that is resolved by using probability. Okay, great. So I would like to distinguish, before I continue, between two different notions. Algorithmic randomness and statistical randomness. Both of which play a role in the study of algorithms, but in very different ways. So algorithmic randomness looks like this. For an arbitrary problem instance, so someone hands you 3 matrices, or someone hands you a matrix, and they ask you a question about it. The algorithm flips coins, which is to say that it draws some random variables. We're not going to talk about where it gets them. Maybe it calls its mom on the phone or something and asks. The algorithm flips coins and uses the outcomes in the computational procedure. Okay, so that's what's happening here. We flip some coins, literally, and then we use the outcomes, which are tabulated in this vector x, inside this algorithm. Same thing here. We drew a normal vector, maybe by starting with some uniforms and applying the Box-Muller transform, whatever. We got some normal variables, and then we ran them through this machine to get an estimate for the maximum eigenvalue. Okay? So that's what we mean by flipping coins and using the outcomes. Okay? These algorithms work for every problem instance. Okay? So there's not any randomness in the instance, it's only in the procedure. And when I say work, I do allow the possibility that the algorithm could fail with some small probability. Okay, what's statistical randomness? So this is a totally different way of approaching the study of algorithms, where, for example, we use a probability model for the instances, or for the behavior of the algorithm. Behavior spelled the other way. Okay. So statistical randomness involves things like random problem instances. So the idea now would be, I believe that my data was drawn from some distribution, and now I'm going to try and fit a model to that data. Okay? This is a lot different from the setting here where someone just says, I'm going to go into my basement laboratory and cook up the worst A, B, and C that I can, and I'm going to ask you to solve this problem. Here, we assume that somehow nature is smiling on us and is generating these from some distribution. Okay? So this is often called average case analysis, and we're not doing this. Okay? We are not analyzing the typical behavior of, or the typical difficulty of problem instances. We are analyzing worst case problem instances. Another thing that you could do is ask about sensitivity to random perturbations. So the idea being that someone hands you some problem instance, you poke it a little at random, and you ask whether that problem instance is easier or harder or something like that. So this is called smoothed analysis. And we're not doing this either. But smoothed analysis actually does have applications in the design of algorithms, in the sense that if you know that nearby problems are easier, you could just take your problem and poke it and solve the nearby problem instead. So perturb it slightly, make your life better. We're not doing that either. Okay. Third thing we're not doing is something like analysis of rounding errors. We talked a little bit about this when Justin mentioned dithering. So one way that people try and understand the behavior of an algorithm is by modeling difficult to understand parts of his execution using probability. So for example, as you know, when you make computations in floating point arithmetic, you make mistakes. Now, how do you model those mistakes? Already in 1951, von Neumann and Goldstein were arguing that you could model them at random, and they tried to understand the performance of some linear algebra algorithms in the presence of random rounding errors. So this is making an assumption about the way rounding errors are distributed, which may or may not be justified, but it can sometimes allow you to understand the behavior or what you hope might be the typical behavior of algorithms. So these are all ways that people try and use statistics to understand linear algebra algorithms, and we're not doing any of this stuff. Okay? We're doing this. We are taking an arbitrary problem instance, we're designing an algorithm that uses randomness to try and solve it correctly. Yeah?
Yeah, from the second case that we discussed there, can you give a little bit more concrete example of what would be a perturbation?
Yep. Yeah, okay. So there are a bunch of examples. The simplest one is the problem of Gaussian elimination. So someone hands you a square matrix and asks you to factorize it into a lower triangular and upper triangular matrix. And the problem with this procedure is that you have to divide by diagonal entries, which are called pivots, and those pivots can get big. So surprisingly, if you take the matrix and you perturb all the entries by independent Gaussian variables, when you run Gaussian elimination, the pivots do not get big. And you can prove that. Okay? So that's an example of how you could take a problem that is potentially hard to solve, modify it a little, and get one that does not have the same algorithmic failure modes.
So you perturb basically the parameters of the structure.
Yeah. Okay, more questions? Okay, so this is all backstory to give you some idea about what we're after. So these are linear algebra problems we want to solve. Here are prototypical algorithms. And as I said, the way we're going to structure this discussion is in terms of themes, which are different strategies for designing linear algebra algorithms. And I'm going to show you multiple instances of these themes. so that you can appreciate that they're not just one-offs. Okay. So today we're going to be talking about Monte Carlo approximation in linear algebra. So before I continue with that, let me just pause and ask if there's anything else you want to chat about before we get on with it. Okay, great. So today, Monte Carlo approximation. Okay, what's Monte Carlo approximation? You know any situations where this is used?
Integrals.
Integrals, exactly. So the classic example is integration. Which is often called quadrature in the numerical analysis parlance. So the idea is that you would like to compute an integral of some function f against a probability measure. And the way you're going to do that is by sampling random variables xi that follow that distribution and are independent. And you're going to approximate the integral by the sum of the function evaluated at these random points. Okay, so that's Monte Carlo integration. Okay. So Monte Carlo approximation is actually one of the oldest schemes for numerical computation. Anyone know who invented this? Okay. So there's some early work by Fermi, not for integrals. It was developed more by Ulam at Los Alamos, von Neumann, and Nick Metropolis. So these are all names that you may have seen before. So they were interested actually in building very efficient models for tracking the diffusion of neutrons. You can imagine why they're interested in this. And so they decided that it's too hard to do these calculations exactly, so instead we're going to take random steps in each of the neutron trajectories and see what happens, and hope that those randomly constructed trajectories are somehow a good proxy for the actual trajectories of a bunch of neutrons. Okay, so this is what they were doing. And this was later developed into a method for computing integrals. It is taught in most introductory numerical analysis classes, where it is often derided as being very inaccurate and perhaps not something you should do if you have another alternative. So, okay. So what's the principle here behind this approach? So at the root, we are generating an unbiased estimate for the integral. Which is to say f of x, where x has the distribution of the probability measure here. And so you can check using the law of the unconscious statistician that the distribution of this random variable is exactly the same distribution as the integrand. And the problem is that one sample is probably a terrible estimate for the integral, even though the expectation of the sample is correct on average. And so the idea is that we are going to reduce the variance by averaging. So this is unbiased. And then we perform variance reduction by averaging. Okay, so how many of you are familiar with this approach? How many of you seen this before? Oh, surprisingly few. Okay. All right, so this isn't my focus here, but this is often a way that people encounter the Monte Carlo approximation idea. It can be used to estimate integrals, and there are fancier versions that can be used to estimate harder integrals. So we're going to take the same approach, and we're going to apply it to some linear algebra problems today. So step one is construct unbiased, a cheap unbiased estimator for the quantity of interest. Step two, average to reduce variance. Okay, so this is the Monte Carlo strategy, and we'll see that this allows us to solve some cool problems in linear algebra. Okay, so this is the Monte Carlo approximation strategy. Okay, great. So the first problem that I want to talk about, let me ask if there are any questions on the quadrature before we continue. I'm going to go through all of the details for these other examples. So. Yeah?
Why is it called quadrature?
I can't remember. Sorry. I feel like a failure. Okay. Anything else? All right, good. So what problem are we going to look at? We are going to look at the implicit trace estimation problem. First, so this is a scalar problem. We're going to try and estimate the trace of a matrix. So let A, again, be a positive semi-definite real symmetric matrix. And we are going to assume that we can only access this matrix via matvex. So what does that mean? Someone gives you a vector x, and you can construct the image of x under A. So you can multiply x into A. Okay. I'll talk in just a minute about why this is maybe a reasonable assumption. And now I'll explain our goal. We want to estimate the trace of A, which is the sum of the diagonal entries, with the minimal number of matvex. Okay? This is the way we access the matrix, and we want to access it as few times as possible. Yep.
Stupid question, but we're explicitly assuming that we cannot read the diagram.
That's right. Yeah. If you can do that, you should do that. Okay? Well, let's talk about some examples in just a second where this is a reasonable assumption. Because it's not so obvious that this is a problem you should care about. Okay? So if you can't look at the diagonal, you can only multiply by vectors. You're trying to reduce the number of times you do that and still produce it. Not necessarily the exact trace, but an estimate for the trace. How long have I been talking? Okay, 40. All right. Good. So let's start with a baseline. So can someone propose to me how you would, the obvious way to solve this problem using MapVex?
Standard basis vectors.
Absolutely. Thank you. The obvious solution is that trace of A is equal to the sum from I equals 1 to n of AEI inner product with EI. So how many MapVex is this? That doesn't seem so promising. But it will get us the exact answer. All right. So the question, of course, is can we do better? And before we talk about that, why should you care? Always a good question to ask about anything. If you ask this question in a spirit of inquiry and goodwill. Okay, not like a teenager or something. Okay, great. So there are actually a ton of applications where this kind of thing happens. So the classic application was cross-validation for smoothing splines. So you know if you have scattered data and you want to fit a model to it, you have a trade-off between the smoothness of the model and the fidelity to the data. So how do you pick the smoothing parameter? Okay. So in this context, fitting the smoothing spline involves solving a linear system, AX equals B, where A is a tridiagonal matrix. Okay? And to do cross-validation, you need to find the trace of the inverse of A, where again, A is tridiagonal. So let me emphasize where those parentheses are. And so it's actually not so easy to get the entries of the inverse of a matrix. But if the matrix is tridiagonal, it is not very hard to solve linear systems. Okay? And so that was the initial application. So you can solve linear systems in A inverse efficiently, and the hope is to be able to use those linear solves to find the trace of A inverse. Okay. Should I clarify this more? Okay. Another place that people do this is in network science, putting this in quotes. And this involves things like computing triangle counts, which involves the trace of A cubed, or the Estrada index, which is something like the trace of E to the A. And there are ways to compute these things without explicitly forming the matrices that are cheaper. So MapVex are a cheaper way to get hold of A cubed than actually forming it directly. There are similar things you could do for the exponential. There are also applications in quantum mechanics. So this involves things like computing partition functions of Hamiltonians, computing, I don't know, average free energy, stuff like this. I don't want to talk about this. But there are tons of places where you have access to the matrix via the matrix vector product rather than via the entries. The classic examples are all in numerical PDE, where A is actually the discretization of some differential or integral operator. And so you can apply the integral or differential operator to a vector by solving an ODE or doing some kind of matrix vector product. Okay? So this is actually a totally reasonable thing to try and do. And now the question is, given that primitive, can we do better than the stupid thing that we've already written on the board? Okay. Any guesses of what we are going to do? We're going to sample. And then we're going to average. So let's figure this out. Okay. Okay, so the idea here is due to Girard from 1988, and it was elaborated by Hutchinson in 1980. I don't know, around 1990. And what they proposed is to build a Monte Carlo estimator for the trace. So that's what we're going to do. And then we're going to do a quick analysis. And we're going to see that if we're willing to accept an approximation for the trace, we can destroy this algorithm that we've already written on the board. Okay? So we can do way better. All right. So a vector x, let me emphasize this is a random vector. A random vector x in Rn is called isotropic if the expectation of x times its transpose is equal to the identity. All right? So it says that different entries of x are uncorrelated with each other, and entries that are the same have variance 1. Fair enough? All right. What are some examples? Standard normal. Very good. Any other examples?
Random canonical vector.
A random which vector?
So a random EI where we random.
Oh, yeah. I'm not going to write that one down because those are very spiky. So they're not so good for what we're doing. But it is isotropic. Any more examples? Sorry, one of it at a time? Rademacher, perfect. Uniform, plus minus 1 to the n. Okay, so as compared with the example you described, these both have a lot of randomness in them, which ironically helps reduce the variability of the estimator. Whereas the random EI is very spiky and it behaves extremely poorly in this context. Okay, so here are a couple examples of isotropic distributions. And now I would like you to define the random variable y obtained by taking ax and then taking the inner product with x. Okay, so how many matvects does this take? 1 matvec. So this is something that we can get our hands on in this model. Okay? Good. So the key observation is that the expectation of y is equal to the expectation of x transpose ax. Now, we're going to write this number as a trace. And then we're going to cycle the trace. Okay, so we're just going to move the x star to the other side. So now we have the isotropy tensor of x, the outer product, xx transpose. So what are we going to do now? We're going to use linearity to pull this inside. And when the expectation hits this random vector, times this transpose. It spits out an identity matrix. And so this simplifies to give us the trace. You agree? Okay, so it's an innocuous calculation, but. All right, so in the language of statistics, Y is an unbiased estimator for the trace. So we've fulfilled the first step of our program. With one MapVec, we can get an unbiased estimator for the trace. The problem is it could be garbage. Okay, it's maybe not surprising, right? Like, you know, we're only collecting one piece of information. It might not be good enough. So what do we do to reduce the variance? Altogether, we average independent copies. So we will define a trace estimator. Trace hat, parameterized by the number of samples. And it's obtained by averaging IID copies of this simple estimator Y. Okay? And you should check that this estimator is still unbiased. So the expectation of the trace estimator is equal to the trace. And that's because of linearity of expectation, which is the most important thing to know about expectation. Okay, now the variance of the trace estimator is reduced as compared with the initial trace estimator by a factor of S. So this is a standard calculation using the independence. So you get an S squared in the denominator, which cancels the S terms in the sum. That's why it's 1 over S. And so we see that we've reduced the variance as compared with the initial estimate. So what are some questions that come to mind now? Huh?
Can we do better?
Do better than what?
What it is on the
We can, but that's a whole other conversation. Yes. Please.
How
Yes.
many samples we need?
How many samples do we need? What else?
That's the best X.
Yeah. What choice of X? These are all great questions. And the other question you asked, which is, can we actually do better than this? Well, we don't know what this is yet or how it does, but it is always a good question to ask. Is this optimal? The answer is no, but this is a much more complicated conversation. Yeah.
I'm going a little bit outside of that context, but here we're sort of assuming that the complexity of A times X
Yep.
is the same no matter how we choose X.
Ah, great question.
But in practice, for instance, if I'm solving a linear system,
Yep.
there are cases where solving a linear system with sparse inputs
Yep.
is going to be massively faster than solving with dense inputs.
Yep. True. So we are not accounting for that in this model. We are charging 1 unit for a MapVec with any vector. As you say, for certain kinds of matrices, that might not be a good assumption. And that you might want to design X to take advantage of the properties of A so that you can compute these MapVecs faster. But, yeah.
Do you have works on that in the context of randomized?
So people have worked on structured problems. I would not say that there was anything specifically on sparsity. And one of the reasons is that when you push toward x being very sparse, the variance goes through the roof. Yeah, so there's definitely a tension there. Yes?
Related question. I mean, is there a reason your relative is a mat vector? Because here you really need x transpose ax. Are there situations where one could be cheaper than the other?
Yes, there are. Great question. For the more efficient algorithms, you actually do need matvex, and the quadratic forms are maybe not enough. But today, we're only using the quadratic form, so as you say, that might actually be a more suitable primitive. Mm-hmm. More questions? Yeah?
Properties of A matter?
Oh, well, yeah, that's a great question. Do properties of A matter? The answer is yes. I'm going to do a worst case analysis, though, just to keep things simple. I'll talk a little bit about how the properties of A matter. OK, awesome. So many good questions. So let's try and answer some of them. So the real issue here is that we need to control the variance of y if we want to understand what's going on here. And we're operating within the class of isotropic distributions because we want the estimator to be unbiased. Now, these are both reasonable choices for y. This one is always better than standard normal, however. So we are going to assume that x is drawn from, actually, it doesn't really matter for what we're doing, but we'll assume that x is drawn from the uniform distribution on plus minus 1 to the n. So each entry is an independent Rademacher, independent plus minus 1, equally likely. And you can calculate that the variance of y is exactly equal to the sum over I not equal to j of aij squared. I don't want to do this on the board because it takes a few lines of work. You have to chase down indices. So this is an exercise for you. And this is obviously at most twice the Frobenius norm of A. You agree? The Frobenius norm is the sum of the squares of the entries. Now, to understand whether this is a good estimate for the variance, we want to compare it with the thing we're trying to estimate, which is the trace. So I want to estimate the Frobenius norm in terms of the trace to understand whether these things are comparable. So to do that, we're going to write out the Frobenius norm in terms of eigenvalues. So we know that the Frobenius norm is the sum of the squares of the eigenvalues of A, because A is symmetric. Now, we're just going to bound this by the maximum eigenvalue times the sum of eigenvalues, which we can do because A is positive. Okay, all the lambdas are non-negative numbers, so this is a simple estimate for the sum of squares. Now, what do we have here on the right? That's the trace. What do we have here? This is the spectral norm because the matrix is positive. So this is equal to twice the spectral norm of A times the trace of A. OK, great. So this tells us that the variance is somehow comparable with the thing we're trying to estimate, which is good news. So let's continue. So there will be a break after we're done with this, and then the second part will be a lot shorter. OK, so in other words, the variance of y, using this assumption, over the squared trace of A, why the square? Well, it's because variances are too homogeneous. Okay, so they're quadratic quantities, so we want to make sure that we're comparing with something that has the same scaling. Okay, the variance of y, so y is gone now. So y is linear in A, the variance is quadratic in A, and so we want to make sure that the scalings the degrees match on both sides. So what we've seen is that this is at most 2 times the norm of A divided by the trace of A. All right. Now, I'm going to make a really crude bound here, and then I'm going to answer your question. So what do you know about the norm as compared with the trace for a positive matrix? It's always smaller than 1. So this is at most 2. Okay? So the variability of each of these samples as compared with the thing we're trying to estimate is constant. So these don't fluctuate that much on the scale of the trace. So we'll take advantage of that in a minute. Now, as an aside, we can define the intrinsic dimension of a positive matrix to be the trace divided by the norm of A, and this is a proxy for the rank. Okay? So this is a measure of the number of energetic dimensions in the matrix A. All right? And it really is comparable with the rank. Okay? So this is the reciprocal of the intrinsic dimension. And so it tells us that the higher the rank of the matrix, the less variable is the simple trace estimate. The lower the rank of the matrix, the more variable is the trace estimate. So the worst case is actually trying to estimate the trace of a rank 1 matrix. Okay. You would think that might be easy, but it is not. So that's an aside, but I'm going to just use this bound. Okay. Any questions on the calculations we made so far? Okay. So A matters, but we're going to suppress that. All right. We're almost done now with our analysis. So we want to understand the probability that the trace estimator provides a good estimate of the trace. So the way we're going to do that is by using Chebyshev's inequality, which is cheap and easy. So the probability that the estimate for the trace as compared with the actual trace is bigger than epsilon times the trace. So this is a relative error. Well, this is bounded by the expected square of the left side, which is also known as the variance of the trace estimator, divided by the right side squared. So epsilon squared times the trace of A squared. Now, we know that the variance of the trace estimator with S samples is comparable with the variance of Y. So this is the variance of Y divided by S times epsilon squared times the trace of A. And now we have the quantity that we already calculated. So this is at most 2 divided by S epsilon squared. Okay? Now I'll explain what this means in just a second. Let me leave this on the board. Okay. Okay, any questions on the calculation? Yeah?
Here, epsilon is a relative.
Yeah, epsilon is the relative error tolerance. Mm-hmm. Yep, so we want our estimate to be close to the trace on the scale of the trace. So you should be thinking about epsilon between 0 and 1, although maybe you're happy with an estimate that's 10 times off even. Yeah, why not? It might be useful. Okay, so let's finish the calculation. So the point of all of this is that we get a non-trivial probability bound for the relative error if the number of samples is bigger than 2 times epsilon minus 2. All right. This is surprising because what this tells us is that we can estimate the trace up to a factor of 2, say, for epsilon equal 1/2. So if you want to get the trace up to 50%, it's enough that S is 16 for any matrix. So what does that mean? That means 16 matvects are enough for us to obtain a non-trivial estimate of the trace of any positive matrix. Okay? So the probability here is actually, I mean, if you do that, the probability here is going to be 1. But of course, you can increase S to drive the probability down. Okay? Any questions on what we've done here? Okay, so to recap, using this randomized trace estimator, which takes S matvects, we can approximate the trace of any positive semi-definite matrix using a constant number of matvects by using this randomized estimator, just a constant number. And that compares with n matvects to compute the trace exactly using the naive approach. So that's potentially a huge win for a big matrix when you have this access model. So one warning about this, how do you feel about epsilon to the minus 2? Yeah, it's kind of terrible. Okay, so epsilon minus 2. So if epsilon is equal to 0.1, then epsilon minus 2 is equal to 100. So if you wanted a 10% relative error, you're going to need a lot of matrix vector multiplies. And that's the sort of downfall of this approach, is that it's good at getting mediocre results. It is bad at getting highly accurate results. This is the reason the numerical analysts hate Monte Carlo method so much. Okay, it's because of this epsilon minus 2. Is this an artifact of the analysis? No, it's not. This comes from the central limit theorem. You can't do better with this algorithm. Okay, and so a natural question is, could there be another algorithm that does better? The answer is yes, but we're not going to talk about it. Okay. So in short, we've already seen one application of Monte Carlo averaging to a problem in linear algebra, which I assert is an interesting problem. I didn't really justify that very thoroughly. We're going to take a break now, and we're going to come back and talk about another application of Monte Carlo averaging to another linear algebra problem, this time involving approximating a matrix. All right, let's take a break. Okay, welcome back. So today we have been talking about Monte Carlo approximation methods. So the strategy of Monte Carlo approximation is to construct a cheap unbiased estimator and to average to reduce variance. So we showed a scalar example, which is the trace estimator. The trace is just a number. Now we're going to look at a matrix example. So we can just as well use Monte Carlo approximation for matrices. Okay, so the ideas that I'm going to be talking about today date back in some cryptomorphic form to a paper of Fries, Cannon, and Vempala from 1998. So they were interested roughly in randomized SVD algorithms, but the approach that they took is really closer to to a method for approximating matrices by sampling. So the thing that I forgot to tell you before is that there actually are lecture notes for this actual short course at this link. So if you want to find out more details and get citations for this stuff, look here. I found a lot of mistakes while I was preparing my notes for these classes, so I'll update these within the next couple of weeks to try and clean up the errors. Okay, so what's the setup here for matrix approximation by Monte Carlo? So we're going to be interested in some target matrix B. So this is a thing that we're trying to approximate. And it's going to be a rectangular matrix now. And the idea behind this entire approach is to break this into simpler pieces. So we will write B as a sum over some index j of matrices Bj, where the Bj are simple. So what are some notions of simplicity for matrices? Low rank? What? Sparse? Great. So for example, low rank or sparse. There are other kinds of things you could imagine, but these are the most obvious ones. Okay? So we're going to chop B into pieces that are simpler. Can you always break a matrix B down to a sum of low-rank matrices? Yeah, what's that called? SVD. It's called the SVD. Can you always break a matrix down into sparse matrices? Sure, just by isolating the entries. Great. Quick studies. All right, so we're going to now construct a probability distribution on the indices. So that is a sequence of numbers pj, j ranging from 1 to capital J, where, as usual, pj are non-negative and sum to 1. Okay, so the idea here is that we are going to assign a probability to each one of the summands, which tells us roughly how important it is. So we would like to sample the important ones with higher probability, and we would like to sample the less important ones with lower probability. So for now, we're just going to leave this as a piece of data that needs to be provided. All right, now, when we talked about the Monte Carlo strategy, our goal was to design a cheap, unbiased estimator, and we're going to do that now. So we are going to define a random matrix Y with the distribution. So I should tell you that Y belongs to the same linear space such that the probability that Y takes the specific value Pj inverse Bj is equal to Pj for each index j. So Y randomly selects one of these simple guys and rescales it. All right, that's it. So obviously, Y inherits the properties of the Bj that are shared among them. Makes sense, because it really is just one of these Bjs. So if the Bj are low rank, Y is low rank. If the Bj are sparse, Y is sparse. Okay? So that's what I mean when I say we're looking for a cheap or a simple unbiased estimator. So let's check that this guy is unbiased. I guess I should quickly comment. What is a random matrix? A random matrix is a matrix whose entries are random numbers that might be correlated with each other. Or if you want to get fancy, it is a measurable function taking values in the space of matrices. Whatever. You know it when you see it, right? It's just like an array of random variables. Okay, so we'd like to check what the expectation of y is. How do we compute the expectation of a random matrix? Yeah?
Expectation of each entry.
Expectation entry by entry. Exactly. So that's what this means. We just make a matrix of the expectations of the entries. So what approach are we going to use to compute the expectation in this setting? We're going to use the law of total probability just like we always do. So we're going to sum over j the possible values of y times the probability that y takes those values. So that's the usual formula for expectation, but it's applied entry-wise, and you can check that if you apply this formula entry-wise, you get the right answer. So we can just write this as matrices without any problem. Now what happens next? The pj's obliterate each other. We get the sum of the bj's, which is also known as b. Okay? So y is not only a simple matrix, but it is an unbiased estimator for the thing we're trying to approximate. Okay. Is y a good estimate for b?
If the pj's are small,
If the what?
the pj's are small.
Yeah. Well, that's a great question. So, well, what happens when the PJs are small? Well, these guys get blown up a lot, so that's scary. And I mean, this is in some ways actually a simpler problem. Y, for example, might have rank 1. Do you think that a rank 1 matrix is a good approximation for a general matrix? No, it's terrible. Okay, so we're going to have to fix this problem. So we are going to improve the approximation quality by averaging. So how does this work? We're going to define an estimator, b hat s, to be the average of s independent copies of this simple estimator. Okay, so if each of the y's has rank 1, what's the rank of b hat? In most s. So that's good news. So the approximation might be relatively simple. But because we're averaging these together, we clearly have more flexibility than if we just have one of these simple guys. If the yi have one non-zero entry, how many entries does bs have? S. Okay, so you can see that the approximation still inherits some of the properties that we've isolated here in this decomposition. So this is good news. So we're getting approximations that we hope are simpler in structure, and we also hope that by increasing the number of samples that we're getting closer to the target. All right. So any questions come to mind? Yeah.
So here we assume that we know the BJs.
Yeah, this is all set up. I'm going to give you a specific example in a minute. It's easier to explain this abstractly, which is why I'm doing it abstractly.
And the probability distribution for y was y is one of the BJs multiplied by PJ inverse
Yep.
with probability
Yep.
PJ. Okay.
Yeah, this is data which is provided to you, and the rest of this is the Monte Carlo procedure provided this data.
Can I ask a stupid question? If we have all the BJs, why do we need to estimate BJ?
Well, I'll show you an example. So one reason is you might like an approximation that's simpler. So you've got a dense matrix, you want to approximate it by a sparse matrix. Okay, that's one reason. You've got a full rank matrix, you want to approximate it by a low rank matrix. Things like that. Okay? I'll show you another example later where there's actually a computational reason to do it. Yep, more questions? All right, so what do we want to know here? What are we trying to accomplish? Yeah?
So one example that would come to mind to me is that I would want an estimate that behaves similar to B for whatever I need to use B for. So
yes.
if I need to do something like B times X, I want my estimator to have good approximation of B times X.
Great.
If I want to estimate eigenvalues, I want to be able to estimate eigenvalues.
Yep. I'm going to provide you an error measure that allows you to do both of those things. So how do we measure the error? Well, we want it to be salient. We want the approximation to be useful for the things we're trying to accomplish. Exactly. And the other question, as before, is how many samples? OK. So the way we're going to measure the error is using the expected relative error in the spectral norm. So this is the maximum singular value. And we're going to divide by the size of the thing we're approximating. Make sense? So this puts it on a scale that is relative to the size of the thing we're approximating, and then we'd just like to know how far away we are. So we're going to try and control the spectral norm error. We would like to be smaller than epsilon. And the amazing thing about the spectral norm is it does all sorts of things for you. It controls linear functionals like matrix vector products. It controls singular values. It controls singular vectors. There are all sorts of things that come from having a bound like this. It's very, very powerful. Okay? So we would like to achieve this relative error bound. And I will write down a sample complexity bound in a second. So this controls things like linear functionals, singular values, and singular vectors, so forth. Okay, so a very, very powerful error bound. Okay, so what do we need to achieve this error bound? So we need the number of samples to be bigger than 4 times the maximum of two numbers, epsilon minus 2, variance of y divided by norm b squared. I'll define these terms in a second. Epsilon minus 1 ly divided by norm b times the log of the sum of the dimensions, where Vy is defined to be the maximum of the expectation of y star and the expectation of y star y. Ly is the biggest that y can be in spectral norm. So this is a uniform bound. And Vy is the per sample second moment. So let me explain what all this means. I just wanted to get it down on the board so we could talk about it. So if we want to achieve relative error epsilon, oh, I missed the epsilon minus 2. Sorry. If we want to achieve relative error epsilon, we need the number of samples to be proportional to epsilon minus, oh, the epsilon minus 2 is here. Sorry. Only need 1. If we want to achieve relative error epsilon, the number of samples we need depends on two things. First of all, it depends on epsilon minus 2 times some measure of the variability of the random matrix Y, our simple estimator. What is this measure? Well, this is roughly the second moment. Okay? Now, it looks a little complicated, but the reason is because you can't square a matrix. You have a rectangular matrix. You have to form two different products, and then we have to take the expectation of those things as matrices. All right. And then we have to compute the norm. So if these were numbers, this would reduce to the expected square of y. All right? So there's a generalization of the expected square, or the second moment. And what we see is that this first bound looks very much like the estimate that we developed before for the trace estimator, right? We saw that the number of samples grew like epsilon minus 2. It depended on the variability of the simple estimate. And then we just have this normalization because we've got the relative error. So this is a lot like the trace estimator. The second term here reflects a new phenomenon, which is what happens if some of the summands happen to be unusually large. Okay, so this is usually not so important. And we also pay for a measure of the size of the matrix, so the logarithm of the total dimension. All right. So what this is telling us is that even if we're trying to do Monte Carlo for matrices, and we want to use this complicated error measure, we can still get a very simple bound on the number of samples we need. It only depends on the variability of the thing we're using to approximate, and a uniform bound on that approximation. Although this looks a little bit complicated, these are things you can get your hands on. These require a little bit of linear algebra, and that's it. The same way that we did this computation here, you can do these kinds of computations. It's just a matter of writing it down and cranking through a few lines of linear algebra, like matrix calculations. Same thing here. It's easy to get a uniform upper bound. Okay? And once you have that data, you can activate this theorem without doing any more random matrix theory. So that's the advantage.
Ly looks like a random variable right now, so maybe an expectation.
This is the essential supremum of the norm of the random variable. So it is the biggest it could ever be, no matter what.
So it's a sup over j, or what is it?
No, this is, so it is the, here it's just the sup over j, yeah. Sorry, this is a more general theorem. Y doesn't have to have this form. Sorry. Yes?
Earlier we had variance. Now why do we have second moment? In particular, I'm thinking about the silly special case where my variance is 0.
Yeah, so in most of these matrix settings, you don't win much by using the variance instead, and you get a simpler theorem to use. That's the reason that we're using second moments instead of variance. You can prove the same thing with the variance here. Okay. More questions on this? Okay, so this is actually a major theorem, and it's not so easy to prove. This is something that is in my lecture notes on matrix concentration. It's called the matrix Monte Carlo theorem, and it is a consequence of the matrix Bernstein inequality. I don't want to get into the details of this because it would take us a little too far astray. The point is simply that even in this complicated matrix setting, we have a similar sample complexity bound, which you can obtain using standard computational math tools. And what I'd like to show you is how the sample complexity bound applies in a specific context. Yeah?
So in one dimension, the scalar thing, the second term is dominated by the second one, or it just doesn't?
They are, no, so we were only, remember, in the scalar case, we were just computing variances, like Chebyshev's inequality. Here, we're doing something that's more uniform. So you can actually get probability bounds as well that control the tails. And for those, you really need this. Although it actually, anyway, I don't want to go off on this tangent. Sorry. Anything else? All right. Good. So the upshot here is that we have this sort of general way of trying to approximate a matrix by sampling the pieces, and we have a bound on the sample number of samples we need to obtain a certain relative error. So what I'd like to do in the next 10 minutes or so, sorry to keep you a little late today, the rest of the lectures will be on time. I'd like to show you an example of this in linear algebra computations. So let's start here. So the problem that we're going to try and solve is called approximate matrix multiplication. And the setup is that we are given a matrix A, which is n by d, with d way, way bigger than n. So this is what we call a fat matrix. It's got a lot of columns, and the columns are not so tall. And the goal here is going to be to approximate B, which is the outer product of A with itself. Now, because the inner dimension is so big, you can imagine that this might cost you some work, because the cost of doing this directly is order n squared times d. So you're not so happy about this d here because it's a big number. Okay? The way that we're going to approach this is by using matrix Monte Carlo. And the decomposition that we're going to use is to notice that we can write this outer product as the sum of the outer products of the columns of A and there are a lot of terms here in this sum. Okay? So these are little m by n matrices, and we're adding up d of them. Okay? So we have here on display a decomposition of B into simple matrices, each of which has rank 1. And so it's natural to try and approximate this by sampling. And so the approximation that we get is going to have the form B hat S is 1 over S, sum from I equals 1 to S, of A I K, got this backward, AKI transpose, where Ki are random. So the idea here is that we are going to randomly sample terms here from this series, and we're going to approximate the matrix B by the sum of those randomly chosen rank 1 matrices. That make sense? Okay, great. So now the question is, how do we choose the sampling probabilities? So right now I don't have the PJs that I need here. So any ideas? How would you choose sampling probabilities?
Proportional to the norm?
Yeah, proportional to the norm. So distribution, we want to PJ to be big when BJ is big in spectral norm, because the bigger, so these guys are the BJs. So when a sum and is important, it has a big norm, we should be more likely to include it. Make sense? So we define PJ to be exactly that. It's the norm of BJ divided by the sum over I of the norm of the BI. Okay? And you can check that this is equal to the squared norm of the jth column divided by the Frobenius norm of the matrix A. So if you make one pass over this matrix, you can compute these probabilities. Mm-hmm.
So don't we still have to pay something like D? We have to do this for every column. We're already paying like something like order D.
Yeah, you pay order ND to compute the sampling probabilities if you don't know the if you don't know these AJs in advance. Mm-hmm. For sure. But if you do happen to know the column norms in advance, you might be able to avoid this. So there's situations where all the columns have the same size, in which case you just have to know how many there are, right? Yeah.
Can you interpret the PJs as some sort of importance sampling?
Yes, that's exactly right. You're sampling in proportion to the importance of one of the summands. How do we measure importance? With the norm. Okay? Very simple. And it's very important that we do importance sampling, because if you don't, you get the wrong, you're going to need a lot more samples. Okay? So this choice of probability ensures that Vy is equal to the Frobenius norm of A squared times the norm of B, and it ensures that L of Y is equal to the Frobenius norm squared of A. This is an exercise. So it's very, very easy to compute these quantities. It's just 2 lines of matrix algebra. All right? So there's not a lot of work here. And once you have these, you can activate the theorem to figure out how many samples you need to approximate the matrix. So the matrix Monte Carlo theorem now implies that to get relative error epsilon, it's enough to take the number of samples to be bigger than 4 epsilon minus 2 times n log 2n. I'm doing some simplification here to make this a little more interpretable. Okay? So once you plug these guys in and simplify, you'll see that the number of samples we need in this Monte Carlo approximation of the product is at most n times log of n. Now, if d, the inner dimension, is much, much bigger than n, then you win. Okay? So we only achieve an approximation that is relative. So we're approximating the outer product by a random matrix, which, isn't exact. So we don't get the exact outer product, AA star. We get this other thing, which is only an approximation. The relative error in that approximation is going to be epsilon. And that's true when the number of columns we pick out is proportional to the outer dimension times a log factor. It doesn't depend on d at all. Okay? This is kind of amazing. So no matter how many columns there are, it doesn't matter. All you care about is the dimension of the thing you're trying to approximate. And this is what the Monte Carlo approach gets you. Now, once again, you have this epsilon minus 2 here, which makes you sad. And it tells you that you can't hope to get a very accurate approximation this way. Epsilon 0.1, you need 100x. On the other hand, if you're happy with epsilon equal to 1/2, you're in good shape. Okay? Great. So there are lots of applications of these kinds of ideas in numerical linear algebra. Some things you might have seen before include sparsification of graphs. So how do you replace a graph by a graph with fewer edges that still has a similar connectivity? How you might be familiar with the random features method for approximating kernel matrices. All of these are examples of matrix Monte Carlo techniques. Okay, that's what I wanted to tell you today. I'm sorry that I've run over a little bit. So the upshot here is that we have a simple procedure, construct an unbiased estimator that's cheap, average them together to reduce variance, and we saw 2 different examples, one to estimate the trace of a matrix and another to estimate the matrix product. And there are a bunch of other applications of Monte Carlo and linear algebra that I haven't discussed. Some of them are cited here in the lecture notes. Next time, we're going to talk about algorithms that depend on a random initialization to succeed. All right, thank you so much. I'll see you tomorrow, I hope.